Hello my steel design friends. In this video I'm going to show you the AISC requirements for designing beams that are considered to be compact. I'm going to show you the sections of the specification where you can find the equations, and then we're going to kind of work our way through some of the approaches for this first step into AISC design of beams. So without further ado, let's get started. So the AISC design specification, and we're talking about the 15th edition of the manual here, the rules for flexure all occur in chapter F of the specification. I'm looking in 16.1-44, so F for flexure. That makes sense to me. Why tension is D, I will never know. But that's all right. Okay, we're going to look at, there are lots of different scenarios that have to be considered when designing beams. And the one thing I don't like about the specification is they don't do a real good job of kind of pictorializing what's going on. But I'm going to point to the sections that are relevant to the discussions that we're going to be having over the course of the next 4 or 5 videos. Okay, the video that we're going to talk about second is all about what's happening in F2. Okay, and this is the lateral torsional buckling phenomenon, and this is for doubly symmetric compact I-shaped members and channels bent about their major axis. All right, so compact is kind of a key word and kind of a catch. And I'll show you how we determine if a shape is compact when we get into doing this, but this will be a requirement to use the rules that are here. Okay, for today we're going to start off with, since we've got to explore compactness anyway, we're going to go to F3. And this is for doubly symmetric I-shaped members with compact webs and non-compact or slender flanges. Okay, so we've got a scenario where we have a compact web but the flanges aren't. Okay, and to look at that, we'll be using this formula here. And if you look, it's lambda minus lambda p all over lambda r minus lambda p multiplied by this quantity. Now keep an eye on this formula because we're going to show you another one that's very, very similar to it. And that occurs over here in F4. Okay, so F3 and F4 is what we're going to start with today. This one is for other I-shaped members with compact or non-compact webs, okay, bent about their major axis. So F3 was for compact or non-compact flanges. F4 is for non-compact webs. And like I say, there's a lot going on in all this, but I'm going to turn your attention over to the formula over here that has to do with compression flange local buckling. And if you kind of look, this formula looks a whole lot like the one that we were just looking at as we try to get into that. So we're going to kind of play around with these formulas, and I'll show you the basic formulas for setting all of this up. So yeah, so let's get going. So we'll put the manual away and set this aside. And so here's what's going to happen for this. Okay, for flexure, we're going to be doing phi mn greater than or equal to mu. That should be no surprise. We're going to be designing for moments, and we're going to be looking for nominal design capacity greater than the factored applied loads. Okay, now we're going to be looking at kind of our, for compactness or for compact shapes. This is the relationship that we're looking at. Phi for flexure is 0.9. It's a yielding criterion, so we're going to be taking advantage of that as well. Okay, now here's the thing, and the way that I start to kind of look at this is that we can actually draw a graphic that kind of shows some of these relationships. I'm going to write all the formulas down, and then we'll come back around and say that if the beam is stable, meaning that it's fully braced, okay, meaning it's got some sort of slab or something that keeps the beam from wanting to roll out of plane up to the point that it fails, Mn can be taken as Mp is equal to Z times Fy. Okay, otherwise, Mn is less than Mp. Okay, now the question becomes, how do we know? And to do this, we must check something known as compactness. And what compactness is a width to thickness ratio of different elements that we're looking at. And as you saw in sections F3 and F4, you can kind of take a guess that one of the ones we're going to be checking is the flange, and the other one is going to be the web. Okay, so we're going to define these parameters as lambdas, okay, and that's what you saw in the formulas. That's why I wanted to show them to you. Okay, lambda is a width to thickness ratio. Lambda p is an upper limit for compact category, and lambda r is the upper limit for non-compact. And our challenge is to figure out, where is this guy in relation to these two? Is he less than lambda p? Is he between lambda p and lambda r? Or is he greater than lambda r? Okay, now you're kind of looking at me going, well, what in the world does all this mean? Okay, And so what we have to look at is we have to kind of take a look at, for the beams, for these I-beams that we're looking at, we're going to be looking at the lambda for the flange, and we're going to be looking at a lambda for the web. Okay, now a web is considered as a stiffened element because in order for it to buckle or fail, it has to first try to move the webs out of the way. So it's a kind of a restrained member. So anytime we're looking at analyzing the web, we're going to be using H over TW as our property for that. Okay, for the flanges, on the other hand, though, the instability occurs on basically the half. This is kind of like a free cantilever that if I fail this or I start to buckle this outer point, only half of the flange is responsible for that phenomenon. And so what we're going to look at is if the whole width is BF and the length of half the width is B, okay, or a half flange dimension, since the flange is unstiffened, there's nothing holding this flange back from wanting to do what it wants to do. Our lambda criteria is, and that's what this is. All of these are lambdas, okay? H over TW for the web and B over TF for the flange. Well, if we know that B is half of BF, then this becomes BF over 2TF, okay? And so these become section properties that we can kind of calculate. Now, you can go through and you can do this calculation based off of the tables of, up in section 1 of our code. So if we flip back to some I-beams that are happening up here, you could go through and you could pull off, H is the whole height of the beam, which would be our D parameter, and we've got TW, and I could do that. Or if you look on the second page, right here, these are the compact section criteria, and you look at the values, they've done the calculations for you. All right, so BF over 2TF and H over TW, and they tallied those values for every shape for the compactness criteria. And so these are your lambda parameters. So we'll check the web, and then we'll check the flanges, and best man wins, right? Best beam wins, I guess. Okay, all right, now here's the way that we're going to do this. For beams and for I shapes, lambda P is taken as the value of 0.38 times the square root of E over Fy. And lambda R for the flange is 1.0 times the square root of E over Fy. Okay, so what we do is when we look at the flange, I'm going to take this BF over 2TF value for my beam, and I'm going to compare it to these two calculations, and that will tell me where we are, whether we're compact, non-compact, or partially compact. Okay, for the web, it's a different set. Okay, lambda P for the web is 3.76 square root of E over Fy. Notice the coefficients are different, and notice that this value is nearly 10 times as much as this value. So the flange buckling is a weakness of these beams when we, in terms of the compactness criteria. And then lambda R for the web is 5.7 square root of E over Fy. So the web is significantly higher values for the lambda values that you're looking at. And for the web, I'll be using H over TW to compare that. Okay, so that's kind of where we're going with this. We'll do a couple of calculations, and then I'm going to show you what the criteria means. In the code, if you read through all those pages of code, it basically boils down to a couple of lines. Okay, if lambda is less than lambda P, the shape is said to be compact. Okay, lambda P less than lambda R is partially compact, or sometimes called non-compact. And if lambda is greater than lambda R, it's a slender element. All right, so those are your three checks, and that's how you classify each of them. So you're going to classify the flange, and you're going to classify the web. Okay, whenever you have a compact section where lambda is less than lambda P, this equation here, the nominal moment capacity is equal to MP. Remember, this is your ZX Fy for an I-beam. Okay, so that's what you've seen before. This is the one we've been playing with a lot to this point. Okay, so for non-compact sections, okay, or when lambda equals lambda R, exactly, Mn is going to be equal to Mr, is then going to be Fy minus Fr, okay, all times an S. This is the elastic section modulus. So now we're worried once we get down into those non-compact areas that we're going to, as soon as we hit yield, that it will fail. It doesn't get to develop its full plastic capacity. This is a significant reduction in strength. Okay, and then the partially compact kind of defines the regions between the two. Okay, and this is the case, partially compact being where lambda is between lambda P and lambda R. Now, like I say, in the code, you look at this and you go, what in the world? It's easy if you draw a picture. All right, so what I'm going to do is I'm going to basically make a graph, and I'm going to plot on this axis my lambda criteria, And on this axis, I'm going to plot my M criteria, my moments. Okay. When lambda is less than lambda p, so I'm going to put 3 vertical lines, one at lambda p, one at lambda r. I said 3, it should be 2. One at lambda p, one at lambda r. Okay, and then I'm going to figure out where my lambda is in relation to these points. If lambda is over here, I'm going to call this as region 1. Okay, and this region here is region 2, and this region here is region 3. Okay, and so that's the way that we're going to kind of define that. And our goal is to figure out what region are we in. So I'll check the web and I'll check the flanges. If lambda is less than lambda p for the one that I'm checking, the nominal moment capacity is MP. That's this horizontal line across the top. Okay. If lambda is greater than lambda r, I'm out in region 3. The nominal moment capacity is here. Okay. And that's our moment that is MR. Okay. Everything else is a straight line connection between those 2 points. That's this formula. All this is a linear interpolation of these points. And it's a straight line approximation that defines region 2. Now, from a design standpoint, you never want to be designing a beam out in region 3. I mean, if this thing gets too slender, it basically goes into no strength and it's asymptotic, almost at 0, way out there. Okay, and you're just giving away so much material that you have a stability of your beam that it can basically carry very little load. So what we like to be, the optimal point is we like to kind of be around here, kind of around that region, as close as I can get to that anyway. All right, because if I'm over here, your beam is so over-designed that you're paying a lot of extra money for a really heavy member that's not needed. Whereas if I'm over in this region, it's a little bit more economical. This is the most economic spot to be kind of looking at on there. But those are the formulas that we're looking at. So Mn here is Z times Fy. Mn here is that iterative formula that we have here. And Mn down on this curve is actually some critical stress, kind of like a buckling stress almost, multiplied by Sx. Okay, except that the FCR equation is pi over LBSX times this monstrosity. Okay, in practice, I have never designed for this equation because it's just a bad idea in general to be here. Okay, so while in theory it does exist, and that's the formula that kind of models it, most normal structures, and again, that's what we're looking at in an undergraduate education, we don't ever use this formula. There's a whole lot of other terms that go in. You've got a warping constant, you have a buckling about the x-axis, but it's got a moment of inertia about the y, because the beam is now so slender that it's starting to kind of roll over on itself. We've got, kind of a pi squared thing happening, so there's a buckling-like term in there. And then I've even got GJ, which is kind of a polar moment and a shear modulus running around. So this thing is all kinds of confused. So, if you're in my class, we won't be doing anything with that. We're going to be trying to design mostly in region 1 and region 2. But you still got to understand how to figure out where you are in this. Okay, now, you may be looking at this going, well, all right, what do I do if region 1, if the flange is in region 1, but the web is in region 2? In that case, worst case wins. Okay, that if the web is the one that's in region 2, you're going to be using the web parameters in this formula. That's what I was trying to show you back in the specification. If the flange is in region 2, you'll be using the flange lambdas up in here and then calculating your moment off of that. And that's kind of the way that we're going to start to kind of establish our criteria. All right, so I hope that's kind of made some sense to you for kind of the basic compactness criteria. In the next video, we'll start with doing some calculations and kind of show you how to do it, but it's a very simple check that we need to look at. But that's the basics for our compactness criteria in the AISC specifications for this. Okay, so again, a couple of things to remember. I have to do a compactness check to know which moment calculation that I'm in. If you remember in the specification when we were talking about that other one, that lateral torsional buckling and the unbraced lengths, we assumed that everything was compact. And for that meant that lambda was less than lambda p. We were a region 1 problem. What's really happening on all of this, okay, and I'll give you kind of the overall story of all of the flexures. I probably should have done this at the beginning, but I didn't. Okay, is that we're going to be looking at kind of, if I take that graph and I kind of turn it a little bit, such that I'm plotting lambda here, and I have, here's my lambda r, that would be my lambda p, and this is my lambda r that happens there. And if I plot the moment on this axis, then on this line, this would be MP. So I'm kind of drawing it in kind of a 3D kind of thing happening here, and then it comes down okay? And then it does that, and so this was my region 1, this is my region 2, this is my region 3, okay, and this is my compactness. What's going to happen is, remember the assumption we made in all of this, that in this plane it was fully braced. And the way that we write that is that LB is equal to 0. And the glare is horrible. Let me pull that page down. That should help us see things a little better. Okay, all right? Okay. On the other axis, then, I can draw this way. We can plot LB. Well, what happens if LB isn't 0? Okay, and you'll start to see, and we'll talk about this when we get to lateral torsional buckling, you get another set of curves that look something kind of like this, and then down here, this gets listed as an LR, this gets listed as an LP. Okay, and so the two simple cases that we're going to work on is this section was F3, F4. Okay, this side was F2. Okay, but in reality, what happens if you're neither one of these pure simple cases? Well, this is actually kind of a three-dimensional, there's my MR moment. This was, MP, and it's MP on both sides. And this guy goes into some MR value that you actually get kind of this three-dimensional solid surface that kind of runs around like that. Okay? Everything out here that isn't on this axis for LB, what's happening here, this requires that lambda is less than lambda P. Or if you want to say that lambda is 0 for compact, you can. And over here it was LB was 0, but we didn't know the compactness criteria. Everything out here is called as a plate girder. Okay, and there are a lot of design procedures and requirements that go into designing for a beam that's not in one of these two simplified cases. Okay, and realistically, in most undergraduate educations, you don't cover this, but if you get to go to grad school, a lot of times we spend a lot of time kind of going over how do you design a plate girder when we're looking for instabilities in the web and in the flanges and stiffeners and all sorts of stuff. But this is kind of the picture that happens. So the picture that I showed you here, that graphic right here is the exact same curve as what you saw on this axis here. It was this line and that line and this line. It's the exact same curve. Okay, and so that's the way we look at it. It's just that now we're going to draw curves for this one, as well as when we get to lateral torsional buckling and unbraced length, we'll be drawing another one that's similar with some other values. But it's very, very similar. So if you can remember this graphic, it will tell you the story. So everything is about figuring out what region are you in as we start to do that. So a little bit of a side note on that. So I hope it's made sense to you. Again, as always, this is a little bit of a shorter video. We'll do some more design examples here in the coming days. But I hope it's made sense to you. If you got any questions, leave them down in the comments down below, and I'll be happy to get back with you. And as always, if you found it useful, please like or subscribe to the channel and like the video, and we will see you guys next time. Happy engineering.